the largest stars we know, would completely engulf our planet's orbit. Some of these colossal suns are so immense, their sheer scale truly challenges the imagination. Take a star like Uy Scuti, for instance, a red hypergiant that boasts a radius over 1,700 times greater than our own Sun. If you could somehow place Uy Scuti right at the center of our solar system, its outer edges would stretch far beyond Jupiter's path. Imagine that, a single star so huge it would swallow 4 of our gas giants and all the rocky worlds within. Even slightly smaller, but still massive, supergiant stars, such as Betelgeuse or Vy Canis Majoris, would easily consume Earth's entire orbital path. They are so vast, our world would simply disappear within their bloated, fiery atmospheres. These enormous stars, these stellar behemoths, are not common across the cosmos. They are quite rare, actually, living incredibly brief lives. They consume their nuclear fuel at a furious pace, burning through their hydrogen and helium in just a few million years. This is a blink of an eye compared to the billions of years our ordinary sun will quietly shine. Their atmospheres are often turbulent and unstable, constantly shedding material into the surrounding space. This shed gas forms enormous, billowing clouds that drift outward, much like smoke rising from an immense fire. The sheer, overwhelming size of these stellar giants offers a powerful reminder. Our Sun, which seems so huge and dominant in our sky, is really quite modest when compared to the truly colossal suns scattered throughout the vast expanse. While most stars glow with a familiar kind of brightness, certain rare giants, like quasars and hyper-luminous stars, can pump out an astonishing amount of energy. They sometimes rival, or even surpass, the total light coming from billions of suns combined. It's a truly mind-bending concept to think that just one object could shine brighter than an entire collection of galaxies. Consider stars like Eta Carinae, for instance, a luminous blue variable. This star releases so much energy, it actually competes with the brightness of small galaxies. Back in the 1800s, Eta Carinae had a massive eruption. It briefly became the second brightest star visible in our night sky. That's pretty wild, especially when you remember it's over 7,000 light-years away from us. Stars like Eta Carinae live incredibly risky lives. They burn through their hydrogen fuel at an unbelievable pace, often ending their existence in a spectacular, explosive supernova. Their intense light pushes outward with such force that it actually blows away their outer layers. This creates incredibly powerful stellar winds. These winds then sculpt glowing nebulae, which are basically huge clouds of gas and dust that surround these super bright stars. These incredible points of light show us something amazing. Even a single star, for a short period, can really dominate the cosmic neighborhood around it. Now, let's talk about neutron stars. These are the leftovers from giant stellar explosions. When a really big star runs out of fuel and collapses, its core might end up as something truly mind-blowing, a neutron star. These objects are tiny, maybe only about 20 kilometers wide, which is roughly the size of a city. But here's the kicker: they pack more mass than our entire sun into that tiny space. The collapse is so extreme, it squeezes atoms together incredibly tightly. Protons and electrons actually merge into neutrons. This creates matter that is denser than anything we know, short of a black hole itself. Imagine this for a second. Just one single teaspoon of material from a neutron star would weigh billions of tons. Seriously, billions of tons. Their surfaces are thought to be incredibly solid, and their gravity is just immense. Their magnetic fields are also ridiculously strong, almost beyond comprehension. Even though they're super small, they beam light across the universe. They do this by sending out radiation, or by heating up their surroundings with any leftover energy from their formation. Neutron stars are kind of like cosmic ghosts. They're the collapsed cores of what used to be massive suns. Now, they're transformed into these incredibly dense, rapidly spinning remnants. They really push the boundaries of what we understand about matter. They show us the astonishing extremes that the universe can create, bending the laws of physics in ways we can barely imagine. Among these neutron stars, there are some that show an even more unbelievable behavior. We call them pulsars. These pulsars spin at absolutely dizzying speeds, often hundreds of times every second. With each spin, they send out focused beams of radio waves or light across space. If one of these beams happens to sweep past Earth, we see a regular pulse. That's why they're called pulsars. The fastest ones, known as millisecond pulsars, can spin over 700 times per second. That's faster than the blades of a kitchen blender. It's truly incredible. These pulses are so incredibly precise that astronomers actually use them as super-accurate cosmic clocks. They can time them with even better accuracy than our best atomic clocks here on Earth. When pulsars were first discovered back in the late 1960s, people even wondered if they might be signals from alien civilizations. Eventually, scientists figured out their true nature. Today, we use pulsars for all sorts of scientific work. They help us test Einstein's theory of relativity, which talks about how gravity works. We even use them to search for gravitational waves, which are ripples in the fabric of space-time itself, traveling across the universe. Pulsars are, without a doubt, some of the most dependable lighthouses we have in the entire cosmos. Then there are magnetars. These are a truly wild type of neutron star. What makes them stand out is their magnetic fields. They are the strongest magnetic fields known anywhere in the universe. A magnetar's magnetic field can be up to 1,000 trillion times more powerful than Earth's magnetic field. Seriously, 1,000 trillion. That kind of power is almost impossible to wrap your head around. It would be strong enough to actually mess with atomic structures, pulling apart molecules and rearranging matter itself. When these magnetic fields suddenly shift, magnetars can let loose enormous flares. These flares release more energy in just a fraction of a second than our sun puts out in hundreds of thousands of years. We've detected these bursts from incredibly far away. Sometimes, for a brief moment, they can even outshine every single star in our entire galaxy combined. Luckily for us, magnetars are pretty rare, and none are close enough to pose any threat to Earth. They act like extreme laboratories in space. They show us what happens when physics is pushed way beyond the limits we could ever hope to recreate here on Earth. You know how we usually picture stars as perfect, round spheres? Well, that's not always the case. Some stars spin so incredibly fast that centrifugal force causes their middle section, their equator, to bulge outward. This flattens them into what we call an oblate, or squashed, shape. A great example of this is the star Achernar. It spins so quickly that its diameter at the equator is actually 50% larger than its diameter from pole to pole. Imagine that, a star that's noticeably wider than it is tall. This rapid spinning can even fling material out into space, creating flat disks of gas around the star. These distorted suns really challenge our usual idea of stars as perfectly balanced, round objects. Instead, they show us that stellar lives can be really dynamic and turbulent. Their shape is influenced by how fast they spin, not just their mass or age. Stars that spin quickly might also mix up their internal layers more effectively. This could actually make them live longer compared to their slower, spinning neighbors. When you see them from far away, they still sparkle like any other star. But up close, they are wildly stretched out by the relentless force of their own incredible speed. Hypergiants, those supermassive stars, can lose more mass than our sun every single year. These hypergiants are among the most unstable and shortest-lived stars in the entire universe. Their enormous size comes with a heavy price. They burn through their fuel so fiercely that their outer layers just can't stay bound to the star. Instead, they shed mass in powerful stellar winds. They can lose more than the Sun's entire mass in just a few thousand years. Take Eta Carinii again, one of the most famous hypergiants. It's surrounded by this huge nebula, a cloud of gas created from all the material it has blasted into space over time. These storms of gas and dust are actually super important. They enrich the galaxy with elements that will eventually form new stars and planets. But for the hypergiant itself, this process is destructive. Its ultimate fate is almost certainly to explode in a violent supernova. It might even leave behind a black hole. These stars are like cosmic firestorms, beautiful and incredibly destructive. They show us the absolute extremes of what a star can be. Now, let's talk about a truly dramatic end for a star. A star that gets too close to a black hole faces an incredibly violent end. The black hole's tidal forces, which are basically the difference in gravity pulling on the near and far sides of the star, can stretch it out like taffy. If the star wanders too close, it's completely ripped apart in an event astronomers call a tidal disruption event. All that stellar material then spirals inward, forming a super-hot, glowing disk as it falls into the black hole. This process releases a massive burst of light. It can briefly outshine all the stars in an entire galaxy combined. Sometimes, powerful jets of material get shot outward at nearly the speed of light, broadcasting this destruction across the entire universe. These events are pretty rare, but they give astronomers a way to study black holes that we usually can't see directly. Each one is a cosmic drama, a brilliant star shredded by gravity's ultimate power. When astronomers see sudden, really intense flashes of light coming from the centers of galaxies, they might be looking at a star getting destroyed by a black hole. These tidal disruption events happen when a star drifts too close to a black hole's immense gravitational pull. It gets stretched so much that it's no longer recognizable. The star's material then forms what's called an accretion disk. This disk heats up to millions of degrees, shining brightly in X-rays and ultraviolet light. These flares can last for months or even years as the black hole slowly devours its stellar meal. The light gradually fades as the star's remnants disappear. Watching these events helps scientists figure out the masses of black holes. It also helps them understand how galaxies change and grow over time. They also serve as powerful reminders that even stars, which seem so immense, radiant, and long-lasting, aren't safe from the deeper forces that shape the universe. Seeing one of these events unfold is like getting a glimpse of gravity's raw, consuming hunger itself. When two stars in a tight binary system spiral closer and closer together, their collision can be one of the most dramatic things that happens in the universe. Specifically, when two neutron stars merge, they release energy not just as light, but also as ripples in the very fabric of spacetime itself. These are called gravitational waves. These waves travel outward at the speed of light, stretching and squeezing space as they go. In 2017, astronomers actually detected gravitational waves from such a collision. Right after that, they saw bursts of gamma rays and visible light. It was the first time ever that humans had observed both gravitational waves and light from the exact same cosmic event. These kinds of collisions also forge heavy elements, like gold and platinum. They scatter these elements throughout the universe. These are the materials that later come together to form planets and, eventually, life. Every ripple of gravitational waves that we detect is like a message from stars colliding unimaginably far away. It's a direct signal from the universe's most violent dance. Not every star stays safely within its galaxy. Some stars get thrown out at such high speeds that they completely escape, drifting alone through the massive darkness between galaxies. These rogue stars can get launched by incredibly violent events. This might include a close encounter with a supermassive black hole or the chaotic breakup of a star cluster. Once they're ejected, they just wander the cosmic void, taking any planets they might have, if those planets survived, into unimaginable isolation. Imagine a single sun, billions of years away from where it was born, traveling endlessly with no galaxy to call home. Even though they're tough to spot, astronomers believe there could be countless intergalactic stars. They're like embers blown from a huge fire, scattered throughout the universe. These stars remind us that space isn't just sitting still, it's full of motion and chance. Even something as huge as a star can be cast adrift in the cosmic ocean. In the very early universe, before galaxies had even fully formed, the very first stars were born. Astronomers call them population Arcturus stars. They were likely absolutely enormous, some hundreds of times more massive than our Sun. Because there weren't any heavy elements around to cool the clouds of gas they formed from, these giants grew super fast. They burned with incredible intensity. Their lives probably only lasted a few million years, which is just a brief flash on cosmic timescales. When they died, they exploded in colossal supernovae. These explosions seeded the universe with the very first carbon, oxygen, and iron. These are the basic building blocks for planets and for life itself. None of these original, primordial stars are still around today, but their fingerprints remain. We can see them in the ancient chemical patterns throughout the cosmos. By studying these clues, scientists are slowly putting together the story of how the first light broke through the darkness. They're figuring out how the universe transformed from being mostly empty hydrogen into a place capable of supporting life. When stars like our Sun reach the end of their lives, they shed their outer layers. What's left behind is a hot, super-dense core called a white dwarf. At first, these remnants shine brightly, glowing with the leftover heat from their past nuclear fires. But over billions and even trillions of years, they slowly radiate away that energy, eventually fading into darkness. The final stage of this process is called a black dwarf. This would be a cold, dead star that no longer gives off any light. However, none of these black dwarfs actually exist yet. The universe itself just isn't old enough for even the oldest white dwarfs to have cooled down that much. The idea of black dwarfs belongs to the extremely distant future, a time when the cosmos will be a much quieter, darker place. They represent the ultimate fate of countless suns. A silent testament that even the most brilliant stars eventually give in to the passage of time. If the universe keeps expanding forever, then its distant future might be a long, slow slide into darkness. Stars will gradually use up all their fuel, and no new ones will form. Red dwarfs, which burn their fuel incredibly slowly, could glow for trillions of years. But even they will eventually fade away. Galaxies will grow dim, planets will freeze solid, and the night sky will eventually empty of starlight. In this vision, sometimes called heat death, the cosmos becomes cold and quiet. All that's left are black holes and the faint, dying embers of dead stars. Even though this future is unimaginably far away, the thought is both humbling and, strangely enough, peaceful. The story of stars has both a beginning and an end. We are alive at a moment when the sky is still bright with their light. To look up now is to witness a universe still in its vibrant, star-filled youth. While our universe might one day fade into darkness, some theories suggest that this isn't the absolute end of the story. Ideas from cosmology propose that our cosmos might bounce, or even give rise to entirely new universes. In those fresh beginnings, the cycle of stars could ignite once more. The elements that were forged in our universe could then seed the next one, ensuring a kind of continuity across cosmic generations. Just like stars die and scatter the ingredients for new stars to form, universes themselves might go through a similar rhythm. They could collapse, be reborn, and renew themselves. Even though this is highly speculative, this concept offers a vision where starlight truly never stops. Instead, it just shifts across scales that are far larger than we can easily imagine. In this view, the stars above us aren't just part of our universe. They're part of a pattern that could repeat endlessly. An eternal dance of light and renewal. Not all stars live fast and die young. The smallest ones, called red dwarfs, burn their fuel so incredibly slowly that they can shine for trillions of years. That's far, far longer than the current age of the universe. These stars are dim and cool compared to our sun, and you often can't see them with your naked eye from Earth. Yet, they are by far the most common stars in the cosmos. They make up the majority of suns in our Milky Way galaxy. Because they live for such an incredibly long time, red dwarfs are fascinating candidates for hosting planets where life could have plenty of time to emerge and evolve. We're talking about timescales that are almost unimaginable to us. None of them have even reached old age yet, simply because the universe itself is still too young. That means the night sky of the far, far future will still be lit by these tiny, enduring embers long after brighter stars like our sun have completely vanished. As the cosmos gets older, the brightest and most massive stars will burn out first. Blue giants and hypergiants, for example, only live for millions of years. Stars like our sun last for billions. But red dwarfs, those small, efficient stars, keep going for trillions of years. Over these immense spans of time, they will become the main light sources in the universe. The galaxies of the distant future might only glow with their faint, red light, making for a softer and much lonelier sky. Eventually, even these incredibly long-lived stars will run out of fuel. They'll fade into white dwarfs and, finally, into black dwarfs. The universe will shift from a bright, star-filled expanse to one lit only by fading embers. It's a vision of a cosmic twilight, where the last stars burn quietly, guiding the universe into its final chapters. For now, though, we are living in its golden age, surrounded by brilliant suns of every size and color. Stars can actually orbit supermassive black holes very closely. At the very centers of galaxies, there are these lurking supermassive black holes. They can be millions to billions of times heavier than our sun. What's amazing is that stars can actually orbit right around them. They trace out paths that really test the limits of gravity. In our own Milky Way, astronomers have watched stars racing around Sagittarius A, which is the black hole at the center of our galaxy. One particular star, named S2, swings within just 17 light-hours of the black hole. That's an incredibly short distance in cosmic terms. When it's closest, it moves at over 5,000 kilometers per second. Watching these orbits allows scientists to measure the black hole's mass with incredible precision. It also helps confirm Einstein's predictions about how gravity actually warps spacetime. These stars manage to survive in a place where we might expect them to be torn apart. It shows that even in the shadow of a black hole, the dance of starlight can continue. When a star gets too close to a black hole, it doesn't always get destroyed. Sometimes, it's actually flung away at tremendous speeds, accelerated by that immense gravity. These are called hypervelocity stars. They can travel at millions of kilometers per hour, fast enough to completely escape their home galaxy. Our Milky Way has several of these runaway stars, speeding outward into intergalactic space. Their incredible journeys might have started near Sagittarius A, where interactions with the central black hole acted like a giant slingshot. For any planets that might be orbiting such a star, the result would be truly extraordinary. A solar system cast adrift, speeding alone through the cosmic darkness. The discovery of these stellar exiles shows us how dynamic galaxies can be. It also reveals how black holes don't just shape what falls into them, but also what gets hurled away. To the naked eye, a star often looks like a single point of light. But in reality, Many stars are actually part of multiple systems. They can be doubles, triples, or even larger groups, all held together by gravity. Binary stars, where two suns orbit a shared center of mass, are especially common. Some pairs are so close that they actually exchange material, while others are so far apart that they only complete one orbit every thousands of years. If you were an observer on a planet orbiting such a system, your sky might feature 2 or 3 suns rising and setting together. Imagine the multiple shadows that would cast. Famous examples include Alpha Centauri, our closest stellar neighbor, which is actually a triple star system. By studying these pairs and groups, astronomers learn a lot about how stars form and how they change over time. What looks like a solitary light in the night sky is often a hidden family, orbiting together in a long, graceful cosmic dance. When a massive star ends its life in a supernova, it doesn't just vanish. It actually reshapes its surroundings in a big way. The explosion sends shock waves rippling into nearby clouds of gas and dust. These shock waves compress the material, which then triggers new waves of star formation. So, in this way, the death of one star can actually kick off the birth of many others. Our own sun might have been born from such an event. Its original nebula would have been enriched by heavy elements scattered by a previous generation of giant stars. These cycles make sure that galaxies stay fertile with starlight, constantly recycling matter into new forms. Every brilliant star that dies leaves behind more than just ashes. It leaves the seeds of future suns, planets, and maybe even life itself. Stars don't simply end. They pass the torch, igniting the next chapters in the ongoing story of the cosmos. While most stars that explode as supernovae have a final, definitive end, a few rare ones defy expectations. In extremely rare cases, a massive star might erupt violently, survive the blast, and then explode again years or even decades later. These unusual events are called pulsational pair instability supernovae. The star becomes unstable, throws out huge amounts of mass, then temporarily settles down. Only later does it finally collapse for good. Such stars shine unpredictably, producing multiple bright outbursts that can sometimes confuse astronomers into thinking they're seeing repeated supernovae in the same location. These exotic stellar deaths highlight just how varied the fates of massive stars can be. They also show us how much more we still need to learn about the limits of nuclear fusion and stellar instability. In cosmic terms, they are stars that seem unwilling to let go, leaving behind a dramatic, flickering record of their struggle against gravity's final pull. Type Ia supernovae are a special kind of exploding star that shine with incredible consistency. They happen when a white dwarf star, which is in a binary system with another star, pulls in too much matter from its companion. This accumulation of mass triggers a runaway thermonuclear explosion. Because these explosions always happen at roughly the same critical mass, their peak brightness is almost uniform across the entire universe. This makes them what astronomers call standard candles. They are reliable beacons that astronomers can use to measure cosmic distances. By comparing how bright they appear from Earth to how bright they truly are, scientists can figure out how far away they must be. Type Ia supernovae played a crucial role in one of astronomy's biggest discoveries, the accelerating expansion of the universe, which is driven by something called dark energy. They aren't just spectacular stellar deaths. They're also fundamental yardsticks that help us understand the sheer immensity of the cosmos itself. Every atom of gold, silver, iron, and calcium that exists on Earth was originally forged in the heart of a star. When massive stars explode as supernovae, they blast those heavy elements out into space, enriching the interstellar medium. Over time, that material becomes part of new stars, new planets, and new living things. Without supernova, the universe would be a much simpler place, mostly filled with just hydrogen and helium. Instead, every explosion spreads the seeds of complexity. The iron in your blood and the calcium in your bones were once carried outward in one of those blasts, drifting through space before eventually finding their way into Earth. Supernovae are violent endings, but they are also incredibly powerful beginnings, scattering the ingredients of life far and wide. In this way, stars are both creators and destroyers. They make sure that the universe is filled not only with light, but with incredible richness and variety. It might sound like something out of a poem, but it's scientifically true. You are literally made of stardust. The atoms that make up your body were forged in stars. The oxygen you breathe, the carbon that forms your cells, the iron in your blood, all of these were created in stellar cores and supernova explosions. Billions of years ago, long before Earth even existed, those elements were just floating in space, waiting for their chance to come together. Carl Sagan famously said, "We are made of star stuff," and that phrase perfectly captures a profound reality. Every human being, every tree, every stone is a collection of recycled stardust. When you look up at the night sky, you're not just gazing at distant suns. You're actually seeing your own origins. The stars gave us the raw materials. And in turn, we are the universe becoming aware of itself. The connection between us and the stars is direct, it's literal, and it's deeply humbling. Iron marks a crucial point where nuclear fusion can no longer power a star. Stars shine because of nuclear fusion. This is the process where lighter elements combine to form heavier ones. This process releases a lot of energy, but there's a limit to it. When a star's core starts to fuse silicon into iron, things change dramatically. Iron doesn't release energy when it's fused. In fact, it actually absorbs energy. This means that once iron starts to build up in a star's core, fusion can no longer hold the star up against its own gravity. At that precise moment, collapse becomes unavoidable. This leads to a catastrophic implosion and often a supernova explosion. The presence of iron is basically a death sentence for massive stars. It marks the point where their fuel runs out in a very fundamental way. It's pretty amazing that this ordinary metal, which we're so familiar with here on Earth, is also the cosmic tipping point that decides when these giants of light will eventually fall. A star is held together by a really delicate balance between two opposing forces. Gravity is constantly pulling all of its mass inward, trying to crush it into a superdense core. At the same time, nuclear fusion, which is the burning of hydrogen into helium in the star's center, pushes outward with heat and radiation. As long as these two forces stay perfectly balanced, the star remains stable. If there's too much outward pressure, it swells up. If there's too little, it shrinks. Our sun has kept this amazing equilibrium for billions of years, and it will continue to do so for billions more. But eventually, when the fuel at its center finally runs out, this balance will tip. The sun will then transform into something completely new. This cosmic tug of war is the fundamental reason why stars exist as steady sources of light, instead of either collapsing instantly or blowing themselves apart. Without fusion, stars would just collapse in an instant. Nuclear fusion isn't just what makes stars shine. It's also what stops them from imploding. Without the outward push of energy from fusion, gravity would crush a star into a dense, collapsed state in mere moments. Even our sun, with its gentle, yellow glow, is balanced on this knife edge every second. The constant fusion of hydrogen into helium keeps it from collapsing under its own immense weight. For larger stars, this balancing act is even more extreme, with truly incredible forces at play. When fusion finally stops, gravity always wins. It pulls the star into a white dwarf, a neutron star, or a black hole. Stars only exist for as long as fusion continues. Their light is a fragile victory against the relentless inward pull of gravity. Some stars burn their fuel 1,000,000 times faster than the sun. Not all stars are as patient as our Sun. The most massive ones consume their nuclear fuel at astonishing rates, sometimes up to 1,000,000 times faster. This means that even though they're much larger and more powerful, they live incredibly short lives, sometimes lasting only a few million years. In contrast, our Sun will shine for roughly 10 billion years. These fast, burning giants blaze with a blue light, pouring energy into space and shaping their galaxies with radiation and powerful stellar winds. Their short lives end violently, often in supernovae that scatter heavy elements throughout the cosmos. The difference between them and stars like our Sun really shows how a star's size dictates its destiny. The bigger the star, the shorter and more dramatic its life. They are like cosmic fireworks, dazzling but incredibly fleeting, while smaller stars remain as steady candles across deep time. Our own Sun, while stable right now, has a pretty dramatic future ahead. In about 5 billion years, it will use up all the hydrogen in its core. As fusion then shifts to helium, the internal balance will change, and the Sun will swell up enormously, becoming a red giant. Its surface will expand outward, likely swallowing Mercury and Venus, and possibly even Earth. The Sun's outer layers will glow a dim red, much cooler than today's golden light, while its core will contract and heat up. Eventually, those outer layers will drift away into space, forming a glowing planetary nebula. What's left will be the core, which shrinks into a white dwarf. Even though this transformation is far in the future, it's a reminder that even stars like our Sun are temporary. They follow paths written into the fundamental physics of fusion and gravity. Our familiar star will one day become something entirely different. The brightest star in Earth's sky is Sirius. On a clear night, Sirius really dominates the heavens. It's also known as the dog star, and it shines almost twice as bright as the next brightest star, Canopus. Part of its incredible brilliance comes from how luminous it truly is, but its relatively close distance, only about 8.5 light-years away, also makes it appear dazzling from Earth. Ancient cultures noticed Sirius for thousands of years, linking it to myths, calendars, and navigation. In ancient Egypt, its appearance in the dawn sky marked the flooding of the Nile River. Today, astronomers know that Sirius is actually a binary system. There's the bright Sirius A, a hot, white star, and then Sirius B, a faint but super dense white dwarf, which was once a massive star itself. To our naked eye, they just blend into one piercing point of light. Sirius is not just bright. It's a reminder that what we see in the night sky often hides much deeper stories. Some stars have names that go back thousands of years. Long before we had telescopes, people gave names to the brightest stars they could see. These names often carried meaning related to agriculture, navigation, or myths. Stars like Betelgeuse, Rigel, and Aldebaran all have names that come from ancient Arabic traditions, while Vega and Altair have roots in ancient Arabic and Latin. In China, India, Greece, and Egypt, stars were woven into stories that helped civilizations understand the sky. Even today, those ancient names still exist, connecting us to people who watched the same sky millennia ago. Behind every familiar constellation lies a rich tapestry of human history, with names passed down through different languages and cultures. While astronomers now use catalog numbers for precise identification, the old names remain, echoing across time. They remind us that our connection with the stars isn't just scientific. It's deeply cultural, stretching all the way back to the very beginning of civilization. Ancient cultures used stars to navigate oceans. Before the invention of compasses and GPS, the stars were incredibly reliable guides. Polynesian voyagers, for example, crossed the vast Pacific Ocean by memorizing the rising and setting points of specific stars. They steered their canoes across thousands of kilometers of open sea. The North Star, which seems almost fixed in the sky, has been used for a very long time in the Northern Hemisphere to find latitude. Arab traders, Greek sailors, and Viking explorers all relied on the celestial map to guide their long journeys. Even the seasonal migrations of people and animals were often timed by the stars. These incredible skills were passed down orally, with songs and stories encoding entire star charts. Navigating by the stars required amazing memory and observational skill, but it worked. Long before modern technology, humans trusted starlight to safely carry them to new lands. Today, those same stars still shine above us, though we now look to them with wonder rather than out of necessity. Polaris is famous as the North Star. It's that one point in the sky that seems to stay put while all the other stars appear to rotate around it. But Polaris hasn't always held this role, and it won't keep it forever. Earth's axis actually wobbles very slowly in a cycle that lasts about 26,000 years. This motion is called precession. It means that the pole star gradually shifts over time. Around 3000 BCE, the star Thuban in the constellation Draco was actually the true North Star. In about 12,000 years from now, the bright star Vega will take its place. Polaris is just the current chapter in a long story of shifting skies. Ancient monuments, like some pyramids and stone circles, were actually aligned to different stars that once held the northern position. Watching the pole star change is like watching Earth slowly breathe across millennia. It's a reminder that even the patterns we rely on in the heavens are always in motion. If you could stand on a distant planet, the constellations you know right now would completely disappear. Stars appear grouped together from Earth only because of our specific viewpoint. If you saw them from light years away, their arrangements would warp into totally unfamiliar patterns. On a planet orbiting Proxima Centauri, our sun would just look like a faint extra star in the sky. From the Andromeda Galaxy, our entire Milky Way would be seen as a glowing band, while the stars we consider familiar would be completely lost in its swirl. This shifting perspective shows that constellations are really just illusions created by distance and angle. The night sky isn't a fixed picture. It's a three-dimensional ocean of suns, and it looks different from every single shore. Imagining other skies makes you realize how deeply our view of the universe is shaped by exactly where we stand within it. The constellations we know, Orion, Cassiopeia, the Big Dipper, they're all temporary. Over thousands and millions of years, stars drift through space. They move relative to one another. Slowly, the familiar patterns will distort beyond recognition. The hunter Orion might lose his belt. The Dipper might lose its handle. Entirely new groupings of stars will emerge. To us, these changes are far too slow to notice in a single lifetime. But on cosmic timescales, the sky is always changing. Future civilizations, or even future species, will inherit skies filled with different maps. The mythology of their constellations will be unique to their time, just as ours are tied to ancient cultures. The constellations we see tonight are just snapshots of a fleeting arrangement. It's a reminder that nothing in the cosmos is truly permanent, not even the patterns we draw in the stars. The light from stars can actually be bent and distorted by gravity, a phenomenon called gravitational lensing. This was a prediction made by Einstein and confirmed over a century ago. When the light from a distant star passes near a massive object, like a galaxy or a black hole, its path can be bent and even magnified. Sometimes, this gravitational lensing can split a star's light into multiple images, or it can make the star appear much brighter than it actually is. Astronomers have even observed individual stars magnified this way, making them briefly visible across billions of light years. Without lensing, those stars would be impossible to detect. It's like nature has its own magnifying glass, allowing us to peer further into the universe than our instruments alone could manage. It shows us that space isn't empty, it's flexible, bending light in ways that reveal hidden treasures. Even the path of starlight is shaped by the invisible hand of gravity. Some constellations will completely disappear in the far future. Constellations are really cultural creations, patterns that we trace on the backdrop of the stars. But they're not eternal. As the Milky Way rotates and stars drift, some of today's most recognizable shapes will vanish. In about 50,000 years, Orion will lose its familiar form. Its bright stars will scatter across the sky. In a few million years, the Big Dipper won't look like a dipper at all anymore. To future observers, these constellations might not exist in any recognizable way. Just as ancient humans saw different skies than we do, future beings will inherit their own unique skies. The constellations we know are simply temporary alignments, and our myths are tied to a passing arrangement of stars. They remind us that the sky itself has a history, and the maps we make of it will someday be as outdated as old charts of the seas. Even though they look fixed, stars are constantly moving. Their immense distances make this motion almost invisible to our naked eye. But over centuries and millennia, these small changes add up. This gradual drift is called proper motion. Barnard's star, for example, visibly shifts its position against the background stars every few decades. It has the fastest known proper motion of any star in the sky. Comparing ancient star maps to modern ones reveals the slow shuffle of the heavens. Even the shapes of constellations change subtly. Our sun didn't always have the same neighboring stars it does now. It's not fixed in one spot either. Our sun actually orbits the center of the Milky Way galaxy, completing one full trip every 200 million years. As it travels, its immediate neighborhood changes constantly. Stars that are close to us today will slowly drift away, and new ones will take their place as they cross our galaxy's path. In the distant past, the sun's closest neighbors were entirely different. Their light mixed with ours in a completely different-looking sky. As the sun keeps going on its journey, the constellations we see around us will transform, and many of the stars we know will eventually fade from our view. This cosmic motion shows us that even our sun's place is temporary. It's just one part of a grand rotation that carries us all around the galaxy. To look at the sky is to see just one snapshot of an endless journey, where our stars' companions come and go across the ages. Globular clusters are these really dense, spherical swarms of stars. They often hold hundreds of thousands of stars, packed tightly into a relatively small space. They orbit the edges of galaxies, almost like glittering satellites. Each one is like a fossil from the early universe. Many globular clusters in our Milky Way are over 12 billion years old, which means they're nearly as ancient as the universe itself. The stars in these clusters are usually small, faint red dwarfs and long-lived giants. The really massive stars would have burned out and died billions of years ago. If you look at a globular cluster through a telescope, it looks like a dazzling snowball made of light. The stars in the center are so crowded that they just blur together. These clusters are more than just beautiful. They're like windows into the past, showing us how the very first stars formed and lived. Studying them is like reading a history book written in starlight, tracing the early days of our galaxy. Hidden among the younger stars in our galaxy are some real elders, ancient suns that date back almost to the very beginning of time. Some of them are over 13 billion years old, nearly as old as the universe itself. These stars formed from primordial gas that had very few heavy elements. Astronomers can identify them by looking at their spectra, which are like fingerprints of the elements in their light. They find signatures that are almost untouched since the Big Bang. Such ancient stars are rare, but they offer crucial clues about the very first moments of star formation, before galaxies had fully matured and heavy elements had filled the cosmos. To look at one of these ancient stars is to peer into deep time, connecting with a survivor from an era when the universe was still incredibly young and mostly dark, just beginning to sparkle with its first starlight. Galaxies are dynamic places. They sometimes collide, merge, or even get ripped apart by gravitational forces. But the stars inside them can actually outlast these dramatic transformations. A star born in a small galaxy might find itself swept into a much larger one after a galactic merger, and it will just keep shining for billions of years. Some stars might even get flung out into intergalactic space, wandering alone long after their original home galaxy has dissolved. In this way, stars can survive events that erase the very structures that created them. It's a reminder that stars are both products of galaxies and also independent entities, continuing on long after galactic boundaries shift. These lone survivors are like cosmic witnesses, living through upheavals on scales almost too vast to imagine. Their light outlasts the cradles that first ignited them. Not all stars shine in isolation. Some are wrapped in mysterious shells of gas and dust. These shells are ejected from their surfaces during times when the star is unstable. These shells can form glowing rings, arcs, or bubbles, all lit up by the star's radiation. The reasons for this can vary. Some stars lose mass through strong stellar winds, while others have eruptions that briefly cause them to swell and shed their outer layers. Often, this material becomes part of intricate nebulae, creating beautiful and sometimes puzzling patterns in space. In some cases, astronomers see multiple shells, which suggests that a star has gone through repeated episodes of shedding. These gas shells don't just decorate the stars. They also enrich the galaxy with elements that will one day form new stars and planets. To study them is to catch a star in the middle of a change, mid-transformation, wearing its own history in glowing veils. Wolf-Rayet stars are rare, massive, and incredibly unstable. They burn so hot and bright that their outer layers are constantly being blown away by fierce stellar winds. These winds can strip away more than 10 Earth masses of material every single year. This creates dramatic halos of gas and dust around the star. Their exposed cores glow with searing heat, often reaching temperatures above 50,000 degrees Celsius. Wolf-Rayet stars are considered to be in a transitional stage, living short, violent lives before they explode as supernovae or collapse into black holes. Despite how rare they are, they play a huge role in enriching galaxies with heavy elements. Their turbulent winds and eventual explosions scatter the raw ingredients for new worlds. They are stars living on the edge, burning so intensely that they can't last long, blazing fiercely before their inevitable end. When a star speeds through space at high velocities, it can actually plow into the surrounding gas and dust. This creates a bow-shaped shockwave in front of it, much like the wake you see behind a boat moving through water. These bow shocks glow in infrared light, which is how astronomers can spot them as arcs or crescents ahead of the star. They tell us both about the motion of the star and the density of the material it's passing through. Such stars are often runaways, ejected from where they were born by explosions or strong gravitational encounters. Their glowing wakes are fleeting, only lasting as long as the star is moving through gas-rich regions. Each bow shock is like a frozen wave in space, a luminous footprint marking a star's restless journey across the galaxy. Not all stars stay tethered to where they were born. Some are ejected from their clusters or galaxies at speeds that can reach hundreds of kilometers per second. These are called runaway stars. They can be launched by supernova explosions that kick them away, or by close encounters with massive black holes. In extreme cases, they can achieve hypervelocity, which is fast enough to completely escape their galaxy. For any planets orbiting such a star, the result would be extraordinary, a solar system hurled alone into the cosmic wilderness. While rare, runaway stars show the chaotic side of the universe, where stellar lives can be suddenly uprooted by violent forces. They streak across the galaxy like cosmic exiles, reminding us that even stars aren't immune to the unpredictability of gravity's games. Newborn stars rarely show themselves right away. They're born inside thick clouds of gas and dust, which are the remnants of the material that collapsed to form them. These dusty cocoons block visible light, hiding the stars from regular telescopes. Instead, astronomers use infrared and radio observations to peer through this veil, revealing clusters of protostars that are still gathering mass. Often, these young stars are surrounded by disks of material that might one day form planets. In time, radiation and stellar winds clear away the dust, and the stars emerge, shining freely. To catch a glimpse of a newborn star is to witness creation in progress. It's a rare and delicate stage that only lasts a fraction of a star's entire life. A star doesn't just start its life by immediately igniting fusion. Before that moment, it exists as a protostar. This is a dense clump of gas that's collapsing under its own gravity. As it contracts, the core heats up, and the protostar glows faintly from gravitational energy alone. During this stage, which can last hundreds of thousands of years, the star gathers material from its surroundings, growing larger and hotter. Jets of gas often stream from its poles, marking its presence in the dark clouds where it's forming. Only when the core temperature reaches about 10 million degrees Celsius does hydrogen fusion begin. That's when the protostar officially becomes a star. This hidden phase is the universe's quiet prelude to starlight, when the future of a sun is still being assembled from darkness. Not all objects in space neatly fit the definition of either a star or a planet. Brown dwarfs occupy this kind of twilight zone between the two. They're too massive to be called planets, but they're not massive enough to sustain steady hydrogen fusion like true stars. They glow faintly with leftover heat from their formation. Some of them briefly fuse deuterium, which is a heavier form of hydrogen, before fading into dim, cool objects. Brown dwarfs can be hard to spot because they mostly shine in infrared light. But astronomers have found many of them, either drifting alone or orbiting other stars. They show us the incredible diversity of objects the universe can create, challenging our simple categories. In a way, they're like failed stars, or perhaps overgrown planets. They remind us that the cosmos often resists simple definitions. Stars aren't always solitary. When two stars orbit close enough to each other, they can actually spiral together and merge. These kinds of collisions release enormous amounts of energy, sometimes producing spectacular outbursts that are visible across the galaxy. When they merge, the stars often become larger, hotter, and more unstable. New layers of nuclear fusion can ignite in their cores. Some mergers might even create rare types of stars that couldn't form naturally otherwise, like blue stragglers. These are stars that appear unusually young because they've been rejuvenated by merging. These events can also leave behind disks of material that might form new planets or simply scatter into space. While violent, stellar mergers are part of the cosmic cycle, reshaping stars into new forms. They remind us that the lives of stars aren't isolated, but interconnected, influenced by neighbors and chance encounters. In many binary star systems, one star actually grows at the expense of its companion. As stars age and expand into giants, their outer layers can spill over onto the other star, pulled by gravity. This process, called mass transfer, can dramatically change both stars' destinies. The star that's receiving the mass might grow hotter and brighter, while the donor star is stripped down to its core, sometimes leaving behind a white dwarf. In extreme cases, the stolen mass can push a star over the limit for stability, leading to a nova or even a supernova. These interactions create some of the most dramatic phenomena we see in the sky, from flickering variable stars to powerful explosions. Binary stars are like cosmic thieves and victims, their lives bound together in relationships as complex and dramatic as any myth, except played out in light and fire across millions of years. Some stars don't just come in pairs, they form trios, orbiting in delicate gravitational dances. Triple star systems can arrange themselves in a few different ways. You might have two close stars, with a third one orbiting much farther out, or all three might be bound in complex, shifting patterns. These systems can create chaotic gravitational effects, which can really influence the motion of any planets that orbit them. In some cases, planets can end up on wildly tilted orbits, experiencing multiple suns rising and setting. Triple systems are fairly common, showing that the universe loves variety. To see one through a telescope is to glimpse an alien solar system, very different from our own, where the rhythms of daylight and night would be nothing like anything on Earth. Such stars reveal that our ordinary solar system is just one possibility among many strange cosmic arrangements. Science fiction often imagines worlds with two suns in their skies, but astronomy actually confirms that they are real. Planets can orbit binary stars in stable paths, circling both suns together. In such systems, a planet would experience really complex day-night cycles with twin sunsets and shifting patterns of light. Other planets might orbit only one star in a binary system, with the companion star rising and setting like an unusually bright moon. NASA has discovered several of these circumbinary planets using the Kepler telescope, proving that these exotic arrangements truly exist. Life under multiple suns would be shaped by cycles unlike anything here on Earth. Seasons, light levels, and even shadows could behave in unpredictable ways. These systems expand our understanding of what's possible, reminding us that the diversity of planetary environments is much wider than our imagination once allowed. Not all stars are scattered evenly throughout galaxies. Some are born in enormous groups. Star clusters can host hundreds of thousands of suns packed tightly into a relatively small region of space. Globular clusters, for example, are so dense that stars in their centers might be only a fraction of a light-year apart. In such crowded environments, stars frequently interact, sometimes exchanging companions or disturbing planetary systems. Open clusters, which are looser and younger, often shine with hot, bright blue stars. Their short lives really highlight the youth of the group. To look at a cluster through a telescope is to see an entire community of stars shining together. It's a reminder that many suns begin their lives not in isolation, but in crowded stellar nurseries. Over time, clusters slowly disperse, their members drifting off to join the galaxy at large. Some clusters are billions of years old, while open clusters typically dissolve within a few 100 million years. Globular clusters can endure for much longer. Many of them are over 10 billion years old, making them nearly as ancient as the Milky Way itself. Their longevity comes from their incredibly dense structure, with gravity binding their hundreds of thousands of stars tightly together. Over eons, the brightest stars die, leaving behind red giants and dense remnants, while dim red dwarfs continue to shine steadily. These clusters orbit the galaxy like relics, survivors from a time when the Milky Way was still forming. Studying them reveals clues about the earliest conditions of galaxy building, as well as the chemical makeup of ancient stars. They are like cosmic time capsules, preserving information about an era that's otherwise long gone. Looking at a globular cluster is like looking back across nearly the entire history of the universe. Open clusters, unlike their globular cousins, are relatively fragile. They form as groups of dozens to thousands of young stars, often within huge stellar nurseries. Over hundreds of millions of years, gravitational tugs from the galaxy slowly pull them apart. Eventually, the stars disperse into the galactic disk, joining the general population of stars. Our own sun is believed to have formed in an open cluster about 4.5 billion years ago, a cluster that has long since dissolved. Even though they're temporary, open clusters provide a snapshot of stellar youth. They're filled with hot, massive stars that illuminate the surrounding gas in brilliant colors. They show that stars are not born alone, but as siblings, companions for a while before scattering into the galaxy to live out their separate fates. While galaxies like the Milky Way form stars at a steady pace, some galaxies go through bursts of creation so intense that they're called starbursts. In these environments, stars are born at rates up to 1,000 times greater than normal. Whole regions blaze with newborn clusters of stars, their combined light pouring out like cosmic fireworks. Starbursts can be triggered by galactic collisions, where tidal forces compress vast amounts of gas into new stars. Even though they're spectacular, these phases are short, lived on cosmic scales, lasting only tens of millions of years. Eventually, the galaxy uses up its gas, and the starburst fades away. These galaxies show us that the universe's rhythms can vary wildly. Sometimes calm, sometimes explosive, but always creative. They remind us that galaxies aren't static collections of stars, but evolving, dynamic systems. Stars are born in giant molecular clouds, which are vast reservoirs of gas and dust that can stretch for hundreds of light years. Within these regions, gravity slowly pulls material into clumps that eventually collapse into protostars. Telescopes reveal these nurseries as glowing nebulae, where young stars shine against the very clouds that birthed them. The Orion Nebula, which you can even see with your naked eye, is one of the closest examples. It's filled with hot, massive stars that illuminate their surroundings. Inside such nurseries, entire generations of stars can form together, creating clusters that later disperse. To peer into a stellar nursery is to watch creation at work, the raw ingredients of the universe assembling into suns that may one day light planets and even life. These clouds are like the wombs of the cosmos, shaping the future skies of galaxies. As new stars grow from collapsing gas, many of them unleash narrow jets of material from their poles. These stellar jets can stretch for light years, plowing into the surrounding clouds and carving luminous trails. This process is thought to help control how the star gathers material. It channels excess energy outward while the rest of the gas falls inward. When observed with powerful telescopes, these jets look like delicate filaments, glowing in pinks and blues. They're lit by shock waves as they collide with nearby gas. Known as Herbig, Haro objects, they are among the most beautiful sights in astronomy, vivid markers of stellar youth. Even though they only last a few tens of thousands of years, they capture the drama of star birth. It's a brief but extraordinary stage before the star settles into long-term stability. Certain stars don't shine with a steady light. Instead, they pulse rhythmically, brightening and dimming. These are called pulsating variable stars. They expand and contract in cycles, driven by changes in pressure and temperature in their outer layers. Some, like Cepheid variables, are so regular that they act as cosmic clocks. Their periods are directly linked to their intrinsic brightness. By measuring their pulses, astronomers can calculate their true luminosity and use them as distance markers across the universe. Others, like RR-Lyrae stars, pulse more rapidly but serve a similar role in mapping the galaxy. To the naked eye, these stars might appear to shimmer strangely, but with careful observation, their beating hearts reveal themselves. Their steady rhythms echo through space, turning stars into natural timekeepers and helping us chart the vastness of the cosmos. We often think of fire as the hottest thing we know, but stars far outshine even our hottest flames. White stars, such as Sirius A, radiate at temperatures of 10 zevallozen degrees Celsius or more. That's way hotter than the bluish flame of burning gas here on Earth. Their surfaces blaze so intensely that they emit light across a wide spectrum, appearing dazzling white or bluish, white to our eyes. These stars are usually more massive and younger than the Sun, and they consume their hydrogen fuel more rapidly. Their brilliance makes them easy to spot in the night sky. Yet, their lifespans are relatively short compared to cooler stars. When we see a white star shining down on us, we're witnessing energy on a scale utterly beyond earthly fire. It's a fusion furnace so hot that even the concept of flames seems small in comparison. Despite their fiery red color, red supergiant stars are surprisingly cool by stellar standards. Their surfaces might only be around 3,000 degrees Celsius, which is cooler than our Sun's 6,000 degrees. But what they lack in temperature, they more than make up for in size. Stars like Betelgeuse swell to hundreds or even over 1,000 times the radius of the Sun. Their vast atmospheres are puffed out into space. If Betelgeuse were at the center of our solar system, it would extend past the orbit of Mars. These stars are nearing the ends of their lives, swollen giants getting ready for an eventual supernova. Their red glow in the night sky is a signal of both greatness and fragility. Though cooler on the surface, they burn ferociously within, shaping their final destiny as some of the most spectacular stellar explosions in the universe. Our own Sun feels incredibly central and unique to us. But in the grand scheme of the cosmos, it's actually an ordinary, middleweight star. It's classified as a yellow dwarf or a G2V main sequence star. It burns steadily, not being especially massive nor especially dim. Billions of stars, just like our Sun, dot the Milky Way galaxy, each one potentially capable of hosting planets. The Sun's ordinariness is actually its gift. It's massive enough to ignite fusion for billions of years, but not so large that it burns out too quickly. This provides a stable, long-term home for life to emerge and evolve. When we look up at the stars, it's comforting to know that our own Sun isn't unusual. If life exists elsewhere in the galaxy, it may very well orbit a star much like ours, steady, yellow, and reliable. Ordinary, in this case, might be exactly what makes it extraordinary. Even though they're faint and hard to see with the naked eye, red dwarfs are by far the most common stars in the universe. Small, cool, and incredibly efficient, they make up perhaps 3/4 of all stars in the Milky Way. Their dim red light means that none of them are visible from Earth without telescopes, despite how abundant they are. Because they burn their hydrogen so slowly, red dwarfs can live for trillions of years, which is much longer than the current age of the universe. This incredible longevity makes them fascinating candidates for hosting habitable worlds, since planets around them would have more than enough time for life to develop. They are the quiet workhorses of the cosmos, far outnumbering the bright blue giants that often grab our attention. The galaxy's glittering fabric is mostly woven from these tiny, enduring suns. At the opposite end of the stellar scale from red dwarfs are blue giants. These stars are dozens of times more massive than the Sun. They burn so fiercely that their lifespans only last a few million years, vanishing in the blink of a cosmic eye. Their rarity comes from this brevity. Even though many might form, they die quickly, leaving only a few scattered across the galaxy at any given time. When they are alive, they blaze with incredible brilliance, often visible across vast distances. Their ultraviolet radiation shapes entire regions of space, ionizing gas clouds and carving out bubbles in the interstellar medium. These stars are like the fireworks of the universe, spectacular, short-lived, and impossible to ignore. To glimpse a blue giant is to catch a rare, fleeting phenomenon, a cosmic titan that will soon collapse in one of the most dramatic deaths imaginable. Stars don't just shine white or yellow. Their light actually spans a full spectrum of colors, from deep crimson to icy blue, depending on their surface temperature. Some stars radiate in shades so subtle that our eyes can't fully perceive them. To us, they might all look bluish or whitish, but through scientific instruments, their true colors become clear, Ultraviolet stars blaze with energies our eyes can't detect, while cooler stars glow in infrared, which is invisible without special sensors. Astronomers map these colors using spectroscopy, which is a technique that splits starlight into rainbows. These rainbows then reveal the star's temperature, composition, and motion. In truth, the night sky is far more colorful than it looks, painted in hues just beyond human vision. The stars we see are only a glimpse of a much richer palette, hidden from us, but blazing across the universe in light of every kind. A star's color isn't just for decoration, it's actually a thermometer for stars. The bluer a star is, the hotter its surface. Blue giants can burn at tens of thousands of degrees, while red dwarfs glow at only a few thousand. Yellow stars, like our sun, fall somewhere in between. This relationship, known as Wien's law, allows astronomers to estimate stellar temperatures just by studying their light. Telescopes equipped with special filters can measure the balance of colors, giving precise readings. The rainbow spread of starlight also reveals details about a star's composition, its motion, and its age. Every star is like a story written in its color, a direct translation of heat into hue. The next time you see a faint red glow or a sharp white sparkle, remember you're looking at a thermometer written in starlight, a cosmic code that astronomers have learned to read. Stars come in a wide range of masses, and the smallest ones live the longest. Low-mass stars sip their hydrogen fuel slowly, converting it into helium with remarkable efficiency. Unlike massive stars, which blaze through their fuel in a few million years, these smaller suns can shine for trillions of years without burning themselves out. Their cooler temperatures make them dim, often invisible to the naked eye from Earth. Yet, they dominate the stellar population of the galaxy. These stars rarely die in dramatic explosions. Instead, they fade gently into white dwarfs, ending their lives quietly. Their longevity and stability make them fascinating targets in the search for habitable planets. Though unimpressive in brightness, low-mass stars are the patient guardians of time, shining long after brighter stars have burned out. The universe began with only the simplest elements: hydrogen, helium, and tiny traces of lithium. Everything heavier, carbon, oxygen, nitrogen, silicon, iron, and beyond, was created in stars. In their cores, nuclear fusion combines lighter atoms into heavier ones, building the chemistry of life atom by atom. When stars die, they scatter those elements into space, where they are incorporated into new stars, planets, and living beings. The oxygen in your lungs and the carbon in your cells were born in stellar furnaces billions of years ago. Without stars, there would be no rocks, no oceans, no DNA. Each element heavier than helium carries the signature of a star that lived and died before us. To study the periodic table is to read the history of starlight, written into the very matter of everything that exists. Some stars actually survive near-death encounters with black holes. When a star passes close to a black hole, the encounter can be devastating. Tidal forces stretch it, and in many cases the star is torn apart. But sometimes, against all odds, the star manages to survive. In these grazing encounters, the black hole strips away only part of the star's outer layers. What's left continues orbiting, battered but still intact, often left distorted or unstable. Astronomers sometimes call these survivors zombie stars, because they carry the scars of near destruction, yet they keep shining. Each passage can strip away more material, gradually feeding the black hole while prolonging the star's agony. These bizarre systems are like natural laboratories for extreme gravity, showing us the razor-thin boundary between survival and annihilation. To imagine a star limping away from a black hole, its light flickering but still alive, is to grasp how finely balanced the cosmic forces of destruction and endurance can be. Galaxies are bustling with stars, but sometimes those stars don't stay put. When two galaxies interact, Their central black holes can play a kind of tug of war, seizing stars from one another. In other cases, stars on the outskirts of galaxies can be stripped away during close passes, stolen by the gravitational dominance of the other galaxy's core. Astronomers have even spotted stars wandering between galaxies, likely casualties of such encounters. The result is that black holes, along with their host galaxies, act as cosmic thieves, gathering and redistributing starlight across intergalactic space. This grand-scale theft reminds us that galaxies aren't isolated islands. They are interacting, evolving structures. The stars we see in the night sky aren't forever loyal to their galactic homes. They are subject to the pull of larger forces, shifting allegiance when gravity demands it. Star clusters can actually sink into galactic centers and feed black holes. Galaxies aren't static, they evolve, and gravity constantly rearranges their structures. Dense star clusters orbiting near galactic centers can slowly spiral inward over billions of years. As they fall, their stars can be torn apart or absorbed into the central black hole. In this way, black holes grow by consuming not just individual stars, but entire clusters. Observations suggest that some supermassive black holes owe much of their mass to these slow, steady feasts. This process also explains why the cores of galaxies are often rich with ancient stars, which are survivors of these migrations. To picture a whole cluster sinking into darkness is to see how galaxies recycle themselves, with black holes acting as engines of transformation. Even though it's destructive, the process helps shape the balance between light and shadow at the hearts of galaxies. When a star gets too close to a black hole, it can be torn apart into streams of gas in a tidal disruption event. Instead of being swallowed all at once, the star's matter is stretched and pulled into a long, glowing stream. This stream orbits the black hole, gradually spiraling inward and forming a disk of gas that's heated to millions of degrees. The process shines so brightly that it can outshine the host galaxy for months or even years. From Earth, these events appear as sudden, powerful flares, like cosmic beacons marking destruction on the grandest scale. Each shredded star is a reminder that even suns, vast as they are, can be unraveled thread by gravity. These ghostly stellar streams arc across the void like ribbons, beautiful and tragic traces of stars undone. Even black holes, which we often think of only as destroyers, can also help create. As material falls into them, some black holes unleash powerful jets of energy that blast outward across their galaxies. These jets compress clouds of gas, sometimes triggering the collapse needed to form new stars. In this way, black holes act as both destroyers and midwives of creation, regulating the pace of stellar birth. Observations of galaxies show regions where star formation is unusually active, and this activity is often linked to black hole activity. The influence of a black hole can extend tens of thousands of light years, shaping the life cycles of stars far beyond its immediate reach. It's a striking paradox. The darkest objects in the universe can play a vital role in spreading new light. Not every star near a black hole is doomed. Some find stable orbits, circling at great distances held fast by gravity but far enough away to avoid destruction. In our own galaxy, astronomers have tracked stars like S2 and S4700 orbiting Sagittarius A, the supermassive black hole at the Milky Way's center. These stars move at incredible speeds, some faster than 7,000 kilometers per second, tracing elegant ellipses that confirm Einstein's theory of relativity. To witness their orbits is to watch gravity in its purest form, stars dancing around a void of infinite pull. Even though they live in perilous neighborhoods, they endure, blazing defiantly while circling a void of immense gravity. They remind us that not every star near a black hole ends in tragedy. Some live out their lives as close companions to cosmic darkness. When stars are young, they are often surrounded by swirling disks of gas and dust. Within these disks, material clumps together, colliding and sticking to form the seeds of planets. Over millions of years, entire planetary systems emerge, sculpted by gravity and the influence of the central star. Astronomers have even captured images of such disks with dark gaps carved by forming planets, proving that we are watching creation in action. Our own solar system began in just such a disk about 4.5 billion years ago. Stars and planets are born together, their fates intertwined from the very beginning. To study these disks is to glimpse the origins of worlds, a reminder that the planets we walk on and the moons that circle them are natural outgrowths of the process that makes stars shine. The most massive stars pour out so much radiation and stellar wind that they carve cavities in the gas and dust around them. These bubbles can stretch dozens of light years across, glowing with ionized gas at their edges. Inside, the powerful radiation clears away material, leaving a hollowed region around the star. When multiple massive stars form together, their bubbles can merge, creating vast, superbubbles that reshape entire regions of a galaxy. These structures aren't just beautiful, they also influence the next generation of star formation by compressing gas at their edges. From Earth, we see them as glowing shells in nebulae, like cosmic balloons inflated by the breath of giants. They show how stars don't simply exist within their galaxies, but actively sculpt them, leaving signatures of their power etched across space. When astronomers see a star's light dim and brighten unpredictably, it doesn't always mean the star itself is changing. Sometimes the cause is dust orbiting nearby, briefly blocking the light as it passes in front. One famous example is Tabby's star, which baffled astronomers with its irregular dimming. The explanation might lie in clouds of dust or debris drifting around it. These flickers remind us that the universe isn't an empty stage, but filled with material that can obscure, scatter, or filter starlight. For distant observers, our own sun might flicker the same way if seen through the dusty plane of the solar system. Such stars teach us humility as sky watchers. What we see is always shaped by the space between us and the light. The brightest stars can sculpt entire nebulae with their radiation. Hot, massive stars radiate such intense ultraviolet light that they ionize vast regions of surrounding gas, making entire nebulae glow. The Orion Nebula, for instance, shines because a cluster of young, massive stars at its heart floods the region with energy. Their radiation pushes back the gas, carving cavities and shaping the delicate filaments of light and shadow we see in telescope images. Over time, this fierce energy disperses the very material from which the stars themselves were born, halting further star formation in their immediate neighborhood. In this way, stars are both creators and destroyers, igniting their nurseries even as they burn them away. These radiant sculptures remind us that light itself has force, shaping the architecture of galaxies on scales that stretch across hundreds of light years. Some stars wander alone through the cosmic void. Most stars live in galaxies, bound together by gravity in vast families. But not all of them stay put. Some stars are flung out by violent events, such as close encounters with black holes or collisions between galaxies. These rogue stars drift alone in the intergalactic void, far from any home. Traveling at hundreds of kilometers per second, they may spend billions of years in isolation. Their light crosses unfathomable distances without ever touching another star system. While lonely, they serve as cosmic messengers, carrying clues about the forces that expelled them. The idea of a single sun wandering through the emptiness between galaxies is haunting. It's a reminder that even stars can be exiled, glowing defiantly against the vast silence of space. Stars are constantly creating the elements inside you. The atoms in your body were forged long before you were born, deep in the hearts of stars. Fusion transforms hydrogen into helium, then helium into heavier elements like carbon, oxygen, and nitrogen. Massive stars take the process even further, building silicon, iron, and beyond. When they die, they scatter these elements into space, enriching future generations of stars and planets. Every breath of oxygen you take, every molecule of carbon in your cells, every trace of iron in your blood, all were once starlight. Stars are like alchemists on a cosmic scale, transmuting simple gas into the building blocks of life. To look at the night sky is to see your own origin story written in glowing furnaces billions of kilometers away. We are, quite literally, the dust of stars carried forward into consciousness. At their core, stars are giant fusion engines. Gravity squeezes hydrogen atoms so tightly that they fuse into helium, releasing energy in the form of light and heat. This process, nuclear fusion, is the same reaction scientists hope to replicate on Earth as a nearly limitless energy source. The balance between gravity pulling inward and fusion pushing outward keeps a star stable for billions of years. Without fusion, stars would collapse under their own weight. With it, they shine across unimaginable distances, powering the growth of galaxies and giving life to planets. When you see a star twinkling, you're witnessing the direct glow of fusion. Atoms merging in a steady blaze that turns the raw material of the universe into brilliance. Stars are proof that the cosmos itself is a kind of laboratory running on reactions that sustain all we know. Hydrogen, the simplest and most abundant element in the universe, is the primary fuel for stars. In stellar cores, the pressures are so immense that hydrogen atoms collide and fuse into helium, releasing bursts of energy with every reaction. This is the fundamental process that makes stars shine. Over time, the buildup of helium changes a star's internal balance, eventually leading it to expand, contract, or transform into new phases of stellar life. In massive stars, fusion can progress beyond helium, creating heavier and heavier elements. But it all begins with hydrogen. Every sunrise is a direct result of this quiet, but relentless transformation. It's a chain of reactions that has burned for billions of years and will continue far into the future. The universe's light, warmth, and chemistry all trace back to hydrogen being squeezed into helium, one fusion at a time. Stars don't last forever, but their deaths aren't the end of the story. When stars explode as supernovae or shed their outer layers, they enrich their surroundings with heavier elements. This gas mixes with the interstellar medium, creating dense clouds. Over time, gravity pulls these clouds together again, sparking the birth of new stars. Every generation of stars carries the heritage of those before it, building more complex chemistry with each cycle. Our sun itself was born from the ashes of earlier stars, carrying within it elements forged in ancient explosions. Future stars will one day emerge from the remnants of ours, continuing this incredible chain. It's a cycle of death and renewal that ensures the galaxy never stands still. Stars live, die, and are reborn, stitching time together with their endless transformations. Not all galaxies form stars at the same pace. In some, called starburst galaxies, conditions are so extreme that stars are born 100 times faster than in the Milky Way. Collisions between galaxies often trigger these bursts, compressing gas clouds into furious waves of star formation. Entire regions blaze with young, massive stars, their radiation flooding space with energy. These galaxies shine brilliantly in infrared light, revealing the intense heat of countless new suns. But this frenzy doesn't last long. After a few 100 million years, the gas is either used up or blown away, and the starburst fades. What remains is a galaxy forever shaped by that brief, chaotic episode. To gaze at a starburst galaxy is to catch the universe in a moment of breathtaking productivity, a cosmic nursery running at full throttle. Not all stars are born equal, and some start their lives with dozens of other suns nearby. Our sun was likely born in a cluster, surrounded by many siblings. For some stars, this crowding is even more intense. In stellar nurseries, dozens or even hundreds of stars can form close together, their gravity tugging and twisting each other's orbits. Some systems end up with multiple suns bound together, while others scatter their siblings over time. Being born in a busy neighborhood means stars can interact dramatically, perhaps stealing planets, flinging companions away, or disrupting each other's growth. Yet, these same environments are where the richest chemistry occurs, as shock waves, radiation, and winds mix material. To imagine a star's first moments is to picture not isolation, but a noisy, glowing nursery where dozens of suns ignite side by side, competing and cooperating in their earliest days. Some dead stars can actually continue to shine for billions of years. When stars like our Sun run out of fuel, they collapse into white dwarfs. Even though they're no longer powered by fusion, these stellar remnants stay hot, glowing with their stored thermal energy. Over billions of years, they slowly cool down, fading ever dimmer. But the timescale is so immense that the universe itself isn't yet old enough for any white dwarf to have completely gone dark. Even dead stars continue to shine, their faint glow marking the graves of suns that once blazed brightly. Observing them allows astronomers to measure the ages of star clusters and trace the history of the galaxy. To see a white dwarf is to glimpse both an ending and a persistence, a star's afterlife glowing quietly long after its fiery youth has passed. Some stars are found in clusters that contain millions of siblings. Certain stars aren't born in small families, but in enormous clusters. Globular clusters, for instance, pack hundreds of thousands to millions of stars into tight, spherical swarms. These ancient groups orbit galaxies like satellites, holding together for billions of years. Their stars are among the oldest in the universe, true relics of an earlier cosmic era. From inside such a cluster, the night sky would be unimaginably bright, filled with thousands of suns across every horizon. Studying these clusters provides insights into how stars change over time, the history of galaxies, and the limits of how gravity can bind things together. They are like natural laboratories where stars live together in extraordinary density, showing us what stellar communities can look like at their most extreme. To stand on a planet in such a cluster would be to see a sky ablaze with starlight. In crowded star clusters, chaos is often the rule. Stars tug at one another, and when one explodes as a supernova, it can dramatically disrupt the gravitational balance. Sometimes this chaos flings stars outward at tremendous speeds, creating what we call runaway stars that hurtle through the galaxy. These stars can reach hundreds of kilometers per second, tracing lonely paths far from where they were born. Astronomers can identify them by their motion, often finding them racing away from clusters or supernova remnants. Runaway stars tell a story of violent beginnings, of gravitational dice rolls that decided their ultimate fate. Even though they're exiled from their crowded homes, they carry with them the memory of explosive origins, their speed a lasting testament to the forces that cast them adrift. Right at the heart of the Milky Way lies Sagittarius A, a supermassive black hole that's about 4 million times the mass of our Sun. What's incredible is that there are stars that orbit it directly. Astronomers have tracked these stars for decades, watching them complete elongated paths around this invisible giant. One star, called S2, gets so close that it whips around the black hole at speeds over 7,000 kilometers per second. Observing these orbits gives us one of the clearest proofs of Einstein's general relativity, as the starlight bends and redshifts in ways predicted by his equations. These stars live in a perilous neighborhood, but they endure, blazing defiantly while circling a void of immense gravity. To watch them is to see a cosmic ballet at its most extreme, suns dancing on the very edge of darkness. Black holes don't just swallow stars, they also bend the space around them in profound ways. Stars caught nearby often find their paths twisted into strange orbits. Some might slingshot around the black hole at dizzying speeds, while others might spiral inward materials. To imagine a star's first moments is to picture not isolation, but a noisy, glowing nursery where dozens of suns ignite side by side, competing and cooperating in their earliest days. When stars like the sun use up their fuel, they collapse into what we call white dwarfs. These are dead stars, essentially. Even though they're no longer powered by fusion, these stellar remnants stay hot, glowing with all the stored thermal energy from their past lives. Over billions of years, they slowly cool down, getting dimmer and dimmer. But the timescale for this is so incredibly vast that the universe itself isn't old enough for any white dwarf to have completely gone dark yet. So, even dead stars continue to shine, their faint glow marking the graves of suns that once blazed brightly. Observing them allows astronomers to figure out the ages of star clusters and trace the history of our galaxy. To see a white dwarf is to glimpse both an ending and a quiet persistence, a star's afterlife glowing softly long after its fiery youth has passed. Some stars aren't born in small families, but in enormous clusters. Globular clusters, for instance, can pack hundreds of thousands, or even millions, of stars into tight, spherical swarms. These ancient groups orbit galaxies like satellites, staying together for billions of years. Their stars are among the oldest in the universe, true relics of an earlier cosmic era. From inside one of these clusters, the night sky would be unimaginably bright, filled with thousands of suns across every single horizon. Studying these clusters gives us insights into how stars evolve, the history of galaxies, and the very limits of how gravity can bind things together. They are like natural laboratories where stars live together in extraordinary density, showing us what stellar communities can look like at their most extreme. To stand on a planet in such a cluster would be to see a sky literally ablaze with starlight. In crowded star clusters, things can get pretty chaotic. Stars constantly tug at one another, and when one of them explodes as a supernova, it can really mess up the gravitational balance. Sometimes, this chaos actually flings stars outward at tremendous speeds, creating what we call runaway stars that hurtle through the galaxy. These stars can reach hundreds of kilometers per second, tracing lonely paths far from where they were born. Astronomers can identify them by their motion, often finding them speeding away from clusters or the leftovers of supernova explosions. Runaway stars tell a story of violent beginnings, of gravitational chance that decided their fate. Even though they're exiled from their crowded homes, they carry with them the memory of explosive origins, their incredible speed a lasting testament to the forces that cast them adrift. Right at the heart of our Milky Way galaxy sits Sagittarius A, a supermassive black hole about 4 million times the mass of our Sun. And incredibly, there are stars that orbit it directly. Astronomers have been tracking these stars for decades, watching them complete elongated paths around this invisible giant. One star, S2, comes so close that it whips around the black hole at speeds over 7,000 kilometers per second. Observing these orbits gives us some of the clearest proof of Einstein's general relativity, as the starlight bends and redshifts in ways that his equations predicted. These stars live in a dangerous neighborhood, but they endure, blazing defiantly while circling a void of immense gravity. To watch them is to see a cosmic ballet at its most extreme, suns dancing on the very edge of darkness. Black holes don't just swallow stars, they also bend the space around them in profound ways. Stars that get caught nearby often find their paths twisted into strange orbits. Some might slingshot around the black hole at dizzying speeds, while others might slowly spiral inward toward destruction. Even stars at safer distances still feel the curvature of space-time, tracing paths that are different from what Isaac Newton's predictions would suggest. Watching these motions has given astronomers a natural laboratory to test the limits of physics. In the center of the Milky Way, these warped stellar orbits reveal the sheer power of Sagittarius A without ever needing to see it directly. For distant galaxies, stars bent into tight swirls confirm the presence of supermassive black holes that are too faint to observe otherwise. The warping of stars is both a map and a signature, the hidden fingerprint of gravity at its most intense. Our Sun feels close and familiar to us, but the next nearest star is still incredibly far away. Proxima Centauri, which is part of the Alpha Centauri system, is over 4 light-years from Earth. That's about 40 trillion kilometers. If a spaceship could travel as fast as the New Horizons probe, which left our solar system, the journey to Proxima Centauri would take nearly 80,000 years. Yet, in cosmic terms, Proxima is our closest neighbor, and it even hosts at least one planet in its habitable zone. To gaze at the night sky is to realize that even our nearest stellar companion is separated by a gulf so immense that light itself takes years to cross it. This perspective makes our Sun feel both more precious and less ordinary. It's just one star among many, but it's also the one that sustains our fragile existence. Our Sun might dominate our skies, but it's only one among hundreds of billions of stars within the Milky Way galaxy. Each of those stars has its own unique story. Some are solitary, some are paired up, some have planets, and some are destined for explosive deaths. The sheer number means that for every star we know, there are billions more quietly burning across the galaxy's spiral arms. Many are smaller red dwarfs, burning dimly for trillions of years. Others are giants, blazing thousands of times brighter than our Sun. From Earth, we only see a fraction of them, even on the darkest nights. To imagine the Milky Way in its entirety is to picture a glowing disk of light so vast that our Sun is just a single grain in its immense sweep.